The darkness between the stars holds secrets that humankind has only just begun to perceive. Amid the silent vastness, an object the size of a city block drifts with a measured grace, utterly impervious to the forces that should dictate its motion. 3I Atlas, our third confirmed visitor from beyond the solar system, moves not as a passive rock shaped by the gravities of nearby planets and the Sun, but as if guided by some hidden intelligence in the void. It vents gas like a conventional comet, the icy plumes illuminated by distant sunlight, yet its trajectory remains curiously unperturbed. Each emission of material, each tiny puff that should push the nucleus along a new path, fails to impart the acceleration that physics demands. The apparent contradiction between visible activity and orbital stasis immediately sets the stage for a mystery that stretches the mind and challenges the assumptions we hold about matter, motion, and the cosmos itself. Imagine the act of firing a garden hose while hovering in zero gravity. The water jets would drive you backward with each expulsion, yet 3I Atlas performs this impossible dance in space, the invisible nozzles of its sublimating ice somehow failing to nudge it off course. It is as if the cosmos has presented a riddle carved from ice and rock, one that balances delicately between the natural and the potentially artificial. Astronomers observing this interstellar visitor find themselves caught between certainty and wonder. The object's coma, a faint halo of gas and dust revealed through the Hubble Space Telescope's piercing vision, glows with the chemical fingerprints of a distant system, yet the anticipated changes in velocity, the tiny nudges that should ripple through its orbit, are conspicuously absent. This opening tableau is more than an anomaly. It is an invitation to question the foundations of celestial mechanics. Newton's laws, tested over centuries and confirmed by every comet that has graced our telescopes, seem insufficient to fully account for what unfolds before our instruments. The very principles that govern rockets, spacecraft, and the dance of planets now appear to falter when confronted with this interstellar visitor. Each observation is a reminder that the universe retains the capacity to surprise, to confound, and to challenge not only the calculations of our astronomers, but the philosophical frameworks through which we interpret the cosmos. 3I Atlas does not merely pass through space, it performs a delicate balancing act, the nature of which is only partially revealed through its glowing plumes, its ghostly anti-tails, and the faint trails of vapor escaping its icy nucleus. These phenomena are measurable, verifiable, and yet paradoxical. The object becomes a bridge between observation and speculation, between what is known and what may yet lie beyond human comprehension. In its silent passage, 3I Atlas whispers the fundamental question that will guide every investigation. How can something be simultaneously active and immovable, alive with motion yet inert in effect? The mystery begins here, in this still, cosmic moment, where the ordinary rules of physics are suspended, and the universe offers a puzzle as profound as it is beautiful. Scale shapes perception, and in the case of 3I Atlas, the scale is staggering. The nucleus, roughly comparable in size to a city block, glides through the inky void with a serenity that belies its violent processes. Every cubic meter of ice and rock contains the potential for immense energy. As solar radiation warms its surface, molecules of carbon dioxide and water vapor escape, streaming into the vacuum with velocities that should translate into measurable momentum. Yet as astronomers track its path, employing high-precision astrometry across continents and through the lenses of Hubble, James Webb, Gemini South, and the Very Large Telescope, the expected deflections fail to materialize. It is as if the very fabric of Newtonian mechanics has been selectively suspended for this interstellar wanderer. The object's venting activity produces a complex, luminous coma, punctuated by subtle plumes and nascent tails that shift with its rotation. Observers are treated to a visual spectacle that is both ordinary and inexplicably alien. A comet's signature features, present yet dissonant with the rules they should obey. The Hubble Space Telescope captures the structure of the coma in unprecedented clarity, revealing streams of gas and dust, while Webb's infrared instruments dissect the composition of the emitted molecules. Gemini South and the Very Large Telescope chart the evolving tail over weeks, detailing the formation of an anti-tail that initially points toward the Sun before transforming into a conventional dust trail pushed outward by solar radiation and wind. The choreography of these features is mesmerizing, a cosmic ballet conducted with precision, yet the underlying physics, the forces that should accelerate the nucleus, remains inscrutably absent. Physically, 3-1 Atlas is a paradox. Massive enough that its inertia resists the push of its own emissions, yet small enough that typical cometary jets, directed asymmetrically, should create detectable non-gravitational acceleration. Its mass, estimated through combining gas production rates, jet velocities, and upper limits on orbital deviation, approaches that of a small mountain condensed into the slender geometry of a comet nucleus. This extraordinary density could theoretically dampen the recoil from escaping molecules, creating the illusion of inertness even amidst intense activity. Yet calculations show that even at such scales, some measurable deviation should appear, unless the object's venting is arranged with near-perfect symmetry. Every plume, every ejection must interact with others in a delicate balance that borders on the improbable. Observationally, the scale of 3-1 Atlas informs not just its dynamics, but its fleeting visibility. Its approach toward Perihelion, expected around October 30th, 2025, brings it to roughly 1.4 astronomical units from the Sun, a distance that allows Earth-bound instruments to detect its activity without risk. The distance preserves its faint luminosity, the soft glow of CO₂-dominated outgassing providing the only visual clue to its internal processes. Its size, combined with the precision of modern observational techniques, transforms the interstellar visitor from a distant point of light into a subject capable of yielding detailed scientific insight. Yet, despite the clarity of data, the visitor's scale underscores the enormity of the challenge, interpreting a phenomenon that appears to operate at the boundary between expected physics and the genuinely anomalous. Thus, the scale of 3-1 Atlas serves dual roles. It is both the physical attribute that may mask the expected effects of outgassing and the narrative lens through which astronomers and the public alike confront the profound strangeness of interstellar space. Observing such a vast object performing what should be an impossible feat forces a reconsideration of assumptions. It reminds us that in the cosmos, size can mute action, mass can obscure dynamics, and even the seemingly ordinary, the slow drift of ice and rock, can conceal mysteries that challenge the most basic principles of motion. In this interplay between mass, momentum, and observation, the enormity of 3-1 Atlas becomes a canvas on which the universe paints one of its most enigmatic portraits. The apparent defiance of Newtonian expectations transforms 3-I Atlas from a curiosity into a profound scientific conundrum. In conventional cometary physics, the rocket effect is inescapable. As volatile molecules escape the nucleus, their recoil produces measurable non-gravitational acceleration, subtly but inexorably nudging the object along a new path. Every comet tracked with sufficient precision, from Halley to 67P Churyumov-Gerasimenko, confirms this immutable rule. The escape of gas and dust is never passive. It is a dialogue between mass and momentum, a constant negotiation of forces that imprints itself on the comet's orbit. Yet, 3I Atlas refuses this dialogue, venting vigorously while maintaining a trajectory that seems to mock the principles underpinning classical mechanics. The strangeness intensifies when the dynamics of its outgassing are scrutinized. Observations reveal plumes that preferentially project in specific directions, measured through time series photometry and spectroscopic analysis. Yet these efforts detect no statistically significant acceleration. The net effect on the comet's path is indistinguishable from zero, within the limits of detection. Astronomers describe this as a non-detection of non-gravitational acceleration, a phenomenon bordering on impossibility. Here is an object simultaneously emitting matter with measurable velocity and producing a null result in the very quantity that should register such activity. In the language of physics, it is a contradiction, an active body behaving inertially. This anomaly is not merely a technical curiosity. It challenges the very frameworks through which celestial mechanics are interpreted. Newton's second law, tested and confirmed across centuries, appears inadequate in predicting the observable behavior of this interstellar visitor. The expected acceleration, derived from measurable gas fluxes, velocities, and estimated mass, should manifest clearly in astrometric data. Yet the absence of detectable orbital deviation persists. The implications are profound. If a natural object can behave in this manner, then the predictive power of established models for active bodies in the solar system and beyond may be incomplete. The possibility arises that other subtle factors, rotation, vent symmetry, surface heterogeneity, or even previously unconsidered physics, may influence dynamics in ways not yet fully modeled. The scientific shock is compounded by the rarity of interstellar visitors themselves. Humanity has catalogued only 3 confirmed interstellar objects, each unique in its behavior. Oumuamua accelerated without visible outgassing. Borisov behaved predictably, and now 3I Atlas presents the converse anomaly: visible activity without measurable acceleration. Within the small statistical sample, these deviations suggest that interstellar space may harbor objects that defy standard expectations, requiring either extraordinary natural circumstances or speculative engineering for explanation. Each measurement, each spectroscopic signature, each observation of tail morphology intensifies the tension between empirical certainty and theoretical expectation. Philosophically, the object embodies the tension between expectation and observation that has always driven scientific advancement. The shock lies not only in the anomaly itself, but in its challenge to the conceptual scaffolding of celestial mechanics. Newton, Einstein, and their successors constructed frameworks to interpret the motions of planets, comets, and spacecraft. 3I Atlas compels astronomers to confront the limitations of these models in real time. The object's defiance evokes both awe and humility, a reminder that the universe remains under no obligation to conform to human assumptions. It becomes a mirror reflecting the provisional nature of scientific knowledge. Even well-tested laws are contingent, subject to refinement when faced with evidence that is both extraordinary and persistent. In this context, 3I Atlas is more than a comet or an interstellar visitor. It is a challenge, a paradox, and a statement from the cosmos. Its refusal to conform is simultaneously a technical problem to be solved and a philosophical prompt to reconsider the nature of physical law. The object reminds us that scientific shock is not merely about discovering the unknown, but about confronting the limits of understanding itself, where each anomaly serves as both puzzle and revelation. The first revelations of 3I Atlas's unusual behavior emerged through the coordinated efforts of the world's most advanced observatories. Hubble's high-resolution imaging provided the earliest glimpse of the comet's evolving coma, capturing sunlight glinting off its ejected gases and dust, forming a faint halo that seemed both familiar and disconcerting. Webb's infrared instruments dissected the spectral fingerprint of its emissions, revealing a predominance of carbon dioxide intermingled with minor water and carbon monoxide, a volatile composition that hinted at a birth in a distant, chemically distinct stellar environment. From the southern hemisphere, Gemini South Observatory and the Very Large Telescope traced the formation and evolution of its tail, documenting a transition from an unusual anti-tail, seemingly pointing sunward, to a more conventional dust trail extended outward by solar radiation pressure. Each observation added nuance, a layer of complexity that both illuminated and deepened the mystery. These instruments revealed a paradox at the heart of the visitor's behavior. While the ejection of gas and dust was evident and measurable, the anticipated orbital deviations remained imperceptible. Detailed calculations of non-gravitational acceleration, informed by precise positional measurements over weeks and months, yielded only upper limits. The signature push that should accompany outgassing the fundamental principle of rocket physics applied to natural bodies was absent. This disconnect between visual confirmation of activity and inertial stasis confounded even the most sophisticated models of cometary dynamics. The observations also captured subtle structural features of the comet's coma and tail that hinted at its internal processes. Sun-facing plumes suggested preferential outgassing from illuminated surfaces, while the faint anti-tail implied a complex interplay of dust particle size, release timing, and orbital geometry. These features were consistent with known physical phenomena, yet their existence underscored the anomaly. If such directed emission was occurring, why did it not translate into measurable momentum transfer? The instruments were not misreading the signals. The activity was real, tangible, and persistent, yet its mechanical consequences were suppressed below detectable thresholds. Hubble's imaging chronologically documented the appearance of the coma, while Webb's spectral analysis quantified the chemical composition in unprecedented detail. The consistency across multiple observational platforms reinforced the reality of the anomaly. Gemini South's long-term tracking of tail structures illustrated evolving dynamics that, in a typical comet, would correlate with detectable acceleration. Instead, 3I Atlas's trajectory remained virtually unchanged, a phenomenon that challenged astronomers to reconcile observable physical processes with the absence of predicted motion. Through these early observations, the comet's mystery expanded. Each dataset, though precise and independently verified, converged on the same fundamental enigma: visible, vigorous activity occurring in the absence of measurable dynamical effects. The convergence across instruments and wavelengths eliminated many mundane explanations: observational error, transient effects, or computational oversight, leaving the scientific community with a single, unyielding question: how could an object manifest the physical signatures of active cometary behavior without producing the motion that such behavior should inevitably generate? This phase of investigation, the initial window opened by the most advanced instruments of human civilization, set the stage for deeper inquiry. It revealed not only the physical characteristics of 3I Atlas, but also the limits of existing theoretical models. By capturing both light and spectrum, motion and morphology, astronomers established a multidimensional portrait of an interstellar visitor that refuses to conform to expectations. It is here, in this convergence of empirical clarity and theoretical shock, that the drama of the 3I Atlas mystery truly begins. To understand the full strangeness of 3I Atlas, one must grasp the concept of non-gravitational acceleration, a subtle yet pervasive force that shapes the orbits of active comets. As volatile ices sublimate, molecules escape from the surface, transferring momentum to the nucleus in a process analogous to a spacecraft firing thrusters. For centuries, this rocket effect has provided a reliable mechanism for predicting cometary motion. As gas jets emerge, they push the nucleus in small, measurable increments, deviations that accumulate over time and can be precisely quantified. Observatories track these deviations using high-precision astrometry, accounting for planetary perturbations, relativistic corrections, and even the gentle pressure of sunlight. The expected result is a direct correlation between activity and acceleration, a principle as fundamental to comet dynamics as Newton's laws themselves. Yet, in the case of 3I Atlas, this principle appears to falter. Observational campaigns spanning months, leveraging Hubble, Webb, and ground-based telescopes, have consistently detected active outgassing, plumes, comas, and evolving tails that betray a volatile, rich surface. Detailed models incorporating gas production rates, vent velocities, and rotational dynamics predict a measurable non-gravitational acceleration. However, the orbital residuals, tiny deviations from the predicted gravitational path, remain at or below detection thresholds. The expected push from vented molecules simply does not appear, leaving scientists confronting a scenario in which known physical mechanisms fail to yield the anticipated effect. This anomaly is unprecedented in the context of cometary studies. Previous interstellar visitors, such as Umuamua, accelerated without visible outgassing, while 2I Borisov behaved entirely predictably. 3I Atlas, however, presents the converse extreme: visible activity without measurable acceleration. The statistical improbability of such behavior immediately captures attention, suggesting either an extraordinarily rare natural circumstance or the intervention of forces yet to be recognized by conventional physics. In practical terms, the discrepancy challenges the calibration of observational techniques, the modeling of vent distribution, and even the assumptions underlying the rocket effect itself. Astronomers are forced to reconsider which variables — mass, vent symmetry, rotation, surface composition — might conspire to suppress measurable acceleration despite vigorous activity. The scientific shock of this phenomenon extends beyond numerical analysis. It raises foundational questions about how small bodies behave when subjected to stellar heating, how momentum transfer scales with size and chemical composition, and whether interstellar objects might follow rules divergent from those derived from solar system comets. Each observation is a reminder that our models, however precise, are provisional. The cosmos retains the capacity to confound expectations, presenting conditions that challenge not only calculations but also the philosophical frameworks within which scientists interpret motion, force, and matter. 3I Atlas thus embodies a tension between known physics and observed reality. Its outgassing is real, measurable, and chemically traceable, yet its motion defies prediction. The paradox is not a subtle deviation but a profound divergence from expectations, a scenario in which classical mechanics encounters behavior that stretches credibility. This is the core of the scientific shock. The object is active yet inert, energetic yet unresponsive, and in that duality, it forces a confrontation with the limits of understanding, inviting both rigorous investigation and cautious wonder. As the anomaly of 3I Atlas became apparent, the first waves of scientific speculation emerged, a spectrum ranging from the entirely natural to the subtly artificial. On one side, researchers proposed explanations rooted in conventional physics, albeit stretched to their extremes. Could the object's mass be so enormous that the momentum from its outgassing is effectively absorbed without detectable acceleration? Might its rotation and distribution of active vents be arranged in such precise symmetry that the thrust from individual plumes cancels almost perfectly, leaving the net trajectory unchanged? These natural explanations rely on the improbable alignment of multiple factors, yet remain within the realm of physics, suggesting that the laws themselves are intact, while the specific circumstances are extraordinary. Parallel to these conventional hypotheses, a more speculative conversation arose, one that flirted with the possibility of artificial intervention. If the symmetry and stability of 3I Atlas cannot be reasonably explained through natural mechanisms alone, could it indicate some form of deliberate stabilization? Concepts borrowed from spacecraft engineering, such as reaction control systems, cold gas microthrusters, or momentum wheels, provide a framework for understanding how an object might actively maintain a precise trajectory while venting matter. In human technology, these principles are employed routinely to counteract external forces, maintain orientation, and regulate motion. Extrapolated to the scale of an interstellar object, they suggest the tantalizing possibility that advanced civilizations could engineer probes capable of traversing the cosmos while maintaining stealth and stability. The duality of interpretation created a philosophical tension as well as a scientific one. Every measurement could be framed within the boundaries of natural processes, yet the improbable combination of activity, stability, and chemical peculiarity invited consideration of alternatives. The nickel-rich, iron-poor signature detected spectroscopically unusual CO₂, dominated outgassing patterns, and apparent mass concentration all contributed to the dialogue. Each anomaly, when considered in isolation, could be reconciled with natural explanations: preferential sublimation, cosmic ray-induced alteration, or formation under exotic conditions in a distant stellar system. Together, however, these features form a constellation of improbabilities, challenging the boundaries of conventional reasoning. This phase of speculation underscores a fundamental principle of frontier science. Anomalies must be approached with both rigorous skepticism and imaginative openness. Extraordinary claims demand extraordinary evidence, yet anomalies cannot be dismissed simply because they stretch expectations. By entertaining both natural and artificial hypotheses, researchers maintain the integrity of scientific inquiry while expanding the conceptual framework necessary to interpret the unprecedented. 3I Atlas becomes not merely an object to be measured, but a catalyst for the evolution of thought itself, forcing astronomers, physicists, and philosophers alike to question which phenomena are strictly natural and which may harbor the fingerprints of intelligence. In the interplay between empirical data and theoretical speculation, 3I Atlas stands as a sentinel at the edge of understanding. Its visible activity without corresponding motion, its anomalous chemistry, and the improbable mass and vent symmetry challenge both instrumentation and imagination. These early speculative hypotheses set the stage for deeper investigation, driving the design of observation campaigns, the refinement of computational models, and the expansion of the very questions that define interstellar research. Here, at the threshold between the known and the unknown, the first philosophical tremors of this cosmic mystery begin to resonate, hinting at implications that reach far beyond mere cometary physics. The story of 3I Atlas's discovery is a tale of patience, precision, and the subtle art of detecting the imperceptible. Long before the object was recognized as an interstellar visitor, months of meticulous sky surveys captured its faint presence, a ghostly point of light drifting against the tapestry of stars. In May 2025, archival images offered only a whisper of its existence, an anonymous speck among billions. It was not until July 1st, 2025, that the Atlas telescope in Chile, designed to monitor near-Earth objects, registered an unusual velocity. Initial calculations revealed a hyperbolic trajectory, a signature that indicated the object was unbound by the Sun's gravity, a cosmic messenger from beyond the solar system. Within days, corroborating observations arrived from observatories across the globe, confirming humanity had indeed detected its third interstellar visitor. The direction of approach added layers of complexity and intrigue. Emerging from the dense stellar fields near Sagittarius, 3I Atlas came from the general vicinity of the galactic center, where the crowded stellar backdrop complicates precise measurements. Observers had to disentangle its motion from countless neighboring photons, threading the needle of astrometry with extraordinary care. Each new observation refined the trajectory, reducing uncertainty and confirming the hyperbolic path that distinguished it from the countless objects bound to our Sunday. This directional signature also carries subtle implications. The object's origins may lie in a region of the galaxy with a distinct chemical environment, hinting at formation under conditions radically different from those of solar system comets. Photometric analysis soon revealed rapid changes in brightness. As 3I Atlas drew closer to the Sun, it developed a characteristic coma, the halo of gas and dust that signaled active sublimation. Early images documented not only the brightening, but the emergence of faint antitail structures, seemingly pointing toward the Sun rather than away. Over weeks, these features evolved, giving way to more conventional tail geometries as solar radiation pressure and the solar wind sculpted the escaping material. Each transformation offered clues to the object's rotation, surface heterogeneity, and volatile composition, yet the fundamental enigma persisted. Despite vigorous activity, the anticipated non-gravitational acceleration remained undetected. The discovery process highlights the interplay of technology, methodology, and cosmic timing. Observatories needed to respond rapidly, coordinating schedules and instrumentation to capture fleeting glimpses of the visitor before it receded beyond observational reach. The detection was not a singular moment, but a continuum of effort, a collaborative achievement combining archive searches, real-time imaging, and sophisticated data analysis. Every photon, every spectral line, and every subtle shift in brightness contributed to a growing understanding, even as it compounded the mystery. In reflecting on the discovery phase, it becomes evident that 3I Atlas's significance lies not solely in its physical characteristics, but in the meticulous narrative it composes across months of observation. It is a story written in light and motion, a message in the interplay between visibility and trajectory. From faint archival detections to confirmed hyperbolic motion, the object emerged gradually, compelling astronomers to confront the limitations of observation, the fragility of expectation, and the extraordinary complexity inherent in studying objects that traverse the interstellar gulf. The discovery, precise yet enigmatic, set the foundation for every subsequent investigation into the nature, composition, and behavior of this remarkable visitor. The Atlas telescope's confirmation of 3180 LAS in early July 2025 marked the moment when observation shifted into scrutiny. The initial images, though limited in resolution, revealed a subtle motion against the stellar background that betrayed the object's interstellar origin. Its hyperbolic trajectory, unmistakable in its departure from the gravitational bounds of the Sun, immediately elevated it from a faint point of light to a subject of intense scientific focus. Observatories worldwide, alerted through coordinated networks, turned their attention to this visitor, each instrument contributing a unique perspective to a developing portrait of a profoundly anomalous object. The approach from the constellation Sagittarius introduced its own observational challenges. Dense star fields complicated the precise extraction of positional data, necessitating repeated measurements and refined calibration techniques. Every photon captured carried significance. Misidentifying a single stellar neighbor could propagate errors that distorted trajectory modeling. Astronomers had to distinguish the motion of 3I Atlas from parallax, proper motion of background stars, and instrumental noise, a painstaking process demanding both technical expertise and patient observation. The accuracy of this global effort allowed for the precise determination of perihelion timing and distance, revealing that the object would pass the Sun at approximately 1.4 astronomical units, safely distant from Earth, yet close enough for detailed study. Beyond trajectory, the early confirmation observations provided hints of the comet's unusual physical behavior. Its rapid brightening suggested active sublimation, the development of a coma, and the formation of complex tail structures. Hubble's July 21st imaging captured the first sun-facing plume, confirming directed outgassing toward the solar hemisphere. Ground-based observatories observed faint anti-tail formations, ephemeral wisps of dust appearing to extend sunward, a visual illusion resulting from orbital geometry and the projection of older ejected material along the line of sight. These features, subtle and transient, illustrated both the capabilities of modern astronomical instrumentation and the delicate interplay between observation, perspective, and interpretation. The Atlas telescope's role was crucial in establishing both discovery and baseline measurements. By providing the initial detection of motion and brightness, it enabled subsequent observations from Hubble, Webb, Gemini South, and other facilities to be targeted effectively, ensuring that follow-up spectroscopy, astrometry, and photometry captured the dynamic evolution of the object. The combination of automated survey detection and rapid human-led confirmation created a pipeline that transformed faint archival specks into a fully recognized interstellar visitor, providing the first concrete opportunity to investigate an object that simultaneously exhibited active cometary behavior and anomalous dynamical properties. In synthesizing these early confirmations, one recognizes the tension between the expected and the observed. Every measurement supports the interstellar identity of 3I Atlas and demonstrates active outgassing, yet none resolves the central paradox of its trajectory. The confirmation phase is therefore both a triumph of observational precision and an introduction to enduring mystery, a comet visible, luminous, chemically active, and yet dynamically inert beyond the predictions of centuries of celestial mechanics. This juxtaposition sets the stage for the deeper investigations that will define the next chapters of understanding, where data and theory must confront the full scope of the impossible. As 3I Atlas approached perihelion, its passage offered astronomers a rare opportunity to study the intricate relationship between solar heating and cometary activity. At approximately 1.4 astronomical units from the Sun, the intensity of incident radiation increased sufficiently to drive sublimation, yet the object remained distant enough to avoid catastrophic disintegration, permitting prolonged observation of its natural processes. The precise geometry of its orbit meant that different regions of the nucleus received varying solar flux, providing a natural experiment in the interaction between rotation, surface heterogeneity, and volatile release. Observers anticipated that activity patterns, jet orientations, and tail formation would reveal the underlying mechanics of the nucleus, offering insights into both composition and structure. Photometric monitoring during this phase revealed a steadily increasing brightness, a clear indication of active material being ejected from the nucleus. The development of a prominent coma, coupled with the emergence of evolving plume structures, confirmed the presence of sublimating ices, particularly carbon dioxide, and suggested that 3I Atlas possessed a heterogeneous surface with discrete active regions. The subtle anti-tail structures, observed intermittently through Gemini South and other ground-based instruments, offered additional clues. They indicated that particles previously ejected remained aligned along the orbital path, producing the visual illusion of sunward-pointing material. These observations demonstrated the sensitivity of visual phenomena to viewing angle, particle size distribution, and the timing of ejection, emphasizing the complexity of interpreting remote imaging in three-dimensional space. Yet the most striking feature remained the absence of measurable non-gravitational acceleration. Despite robust photometric evidence for active outgassing and repeated measurements across multiple observatories, orbital analyses revealed that the comet's trajectory deviated negligibly from predictions based solely on gravitational forces. This lack of expected acceleration highlighted the central paradox. 3A Atlas exhibited all hallmarks of a dynamically active comet, yet defied the fundamental principles that link mass ejection to momentum transfer. The persistence of this anomaly, through successive observational windows, underscored its significance and ensured that it would become a focal point for theoretical investigation. At this stage, astronomers began to explore the interplay of rotational dynamics and vent geometry more intensively. Models suggested that a near-perfect distribution of active regions, combined with rotational states that minimized the directional bias of outgassing, could partially explain the suppressed acceleration. Nevertheless, achieving the degree of symmetry necessary to match observational constraints seemed improbable, raising the possibility that other factors perhaps related to unusual mass concentration or internal structural properties contributed to the observed stability. Each hypothesis required careful validation against the growing dataset, blending computational modeling with empirical evidence in a delicate balance between speculation and measurable reality. The Perihelion approach also sharpened logistical considerations for observation. The proximity to Earth and the changing relative positions of Sun, comet, and telescopes dictated the timing and orientation of imaging, spectroscopy, and astrometry campaigns. Observers leveraged every available instrument, from Earth-based optical and infrared arrays to spaceborne platforms, coordinating schedules to maximize data collection during the brief windows when the comet was optimally visible. These efforts transformed the perihelion passage into a cosmic laboratory, where each photon, each spectral line, and each subtle motion could potentially reveal the mechanics behind one of the most enigmatic objects ever recorded. In this phase, the convergence of observational opportunity and intrinsic anomaly underscored both the beauty and the challenge of studying 3I Atlas, a natural object that stubbornly resisted full comprehension. The chemical composition of 3I Atlas emerged as a central focal point in understanding the anomaly. Spectroscopic analysis, led by the James Webb Space Telescope's near-infrared spectrograph, revealed a nucleus dominated by carbon dioxide sublimation, with water vapor and carbon monoxide playing secondary roles. Unlike most solar system comets, where water is the primary volatile driving activity, the CO2-rich outgassing suggested a formation environment markedly different from our own planetary neighborhood. Such a composition has profound implications. It implies that the venting might occur more isotropically, producing a more balanced thrust profile and potentially explaining the absence of detectable non-gravitational acceleration. The chemical signature itself became both a diagnostic tool and a source of intrigue, revealing the object's origins while simultaneously deepening the mystery of its dynamics. Hubble imaging provided a complementary perspective, capturing the visual evolution of the coma and tail across multiple epochs. The July 21st observation highlighted a sun-facing plume, confirming active venting toward the solar hemisphere, while subtle anti-tail features suggested complex dust dynamics influenced by the geometry of observation and prior ejection history. Ground-based instruments, including the Gemini South Observatory, documented the transition from this anti-tail to a conventional dust trail extending away from the Sun under the influence of solar radiation pressure. These observations, coupled with precise photometry, revealed a consistent increase in production rates of CO₂ and trace elements, further confirming active sublimation and ongoing chemical evolution. Among the chemical anomalies, the detection of nickel without corresponding iron drew particular attention. Historically, nickel and iron appear together in cometary compositions, reflecting their joint synthesis in stellar furnaces and incorporation into planetary materials. The isolated presence of nickel raised questions about formation history, surface processes, or potential technological analogues. Several natural explanations were considered: preferential liberation of nickel, bearing compounds under solar irradiation, differential volatility leading to early release of nickel, and space weathering effects from cosmic rays over millions of years. Yet, the possibility that such a signature could resemble the erosion patterns of high-temperature superalloys, analogous to human-engineered materials, added a speculative dimension that could not be entirely dismissed. The interplay between composition and dynamics became increasingly significant. Carbon dioxide's uniform sublimation across the surface could naturally produce symmetric outgassing, mitigating net thrust and suppressing non-gravitational acceleration. This chemical explanation, combined with considerations of mass and rotational state, provided a plausible natural framework for the observed stability. However, the extraordinary precision required to maintain such balance underlines the peculiarity of 3.1 Atlas. Even within conventional physics, its behavior occupies the extreme edges of plausibility. The chemical evidence thus serves a dual role. It constrains potential explanations while simultaneously highlighting the object's anomalous nature. In this context, spectroscopy is not merely descriptive, but interpretive. Each molecular signature, each emission line, informs models of mass, jet, geometry, and dynamical response. As 3I Atlas approaches perihelion, continuous chemical monitoring promises to refine these models, potentially resolving questions about isotropy of venting, surface heterogeneity, and the relationship between composition and trajectory. Yet, even as natural explanations coalesce around the CO₂-dominated activity and subtle vent symmetry, the object retains a compelling air of mystery. Its chemical fingerprint is both a key and a lock. It illuminates origins, constrains physical mechanisms, and yet preserves the enigma that defines this interstellar visitor. The anomalous behavior and chemical peculiarities of 3I Atlas carry profound implications for the search for extraterrestrial intelligence, prompting a reconsideration of SETI strategies long dominated by electromagnetic observation. For decades, humanity has listened to the cosmos for intentional radio or optical transmissions, from the pioneering Project Ozma in 1960 to contemporary initiatives such as Breakthrough Listen. These programs assume that technologically advanced civilizations will advertise their presence through detectable signals, powerful beacons deliberately transmitted across interstellar distances. Yet 3.1 Atlas challenges this paradigm, suggesting that evidence of intelligence may sometimes be embedded in physical objects rather than broadcast signals. A naturally occurring comet, anomalous in both composition and dynamics, could, if artificially modified or stabilized, represent an alternative avenue for detection, a silent messenger navigating the void. The concept requires a shift from traditional SETI assumptions. Rather than monitoring electromagnetic signals alone, researchers might consider the detailed analysis of interstellar visitors for signatures that defy natural explanations. 3I Atlas offers a case study, a body displaying vigorous outgassing with negligible non-gravitational acceleration, a chemical fingerprint that is unusually CO₂-rich, and a metallic signature nickel without iron that is rare among known cometary populations. Taken collectively, these anomalies form a pattern that cannot be immediately dismissed as mere coincidence. If such features were the product of intentional engineering, they could constitute a form of communication or observational technology invisible to conventional detection methods. This line of inquiry also redefines the temporal and methodological framework for SETI. Unlike transient radio signals, interstellar visitors have finite observational windows dictated by their passage through the solar system. Rapid identification, immediate allocation of telescope resources, and intensive spectroscopic and astrometric follow-up become critical. The integration of orbital dynamics analysis with chemical and photometric studies allows scientists to distinguish between natural and potentially artificial anomalies, expanding the toolkit of the search for intelligence beyond the electromagnetic spectrum. In this sense, 3I Atlas serves as both a challenge and an opportunity. It compels the scientific community to develop protocols capable of rapidly evaluating anomalous objects for signatures of artificial origin. Statistical considerations further enhance the significance of this approach. With only 3 confirmed interstellar objects detected within a decade, 2 exhibiting highly unusual dynamics, Umuamua with acceleration without visible outgassing, and 3I Atlas with activity without acceleration, the probability that such anomalies occur by chance is remarkably low. This suggests either an unappreciated diversity in interstellar object behavior or the presence of systematic factors, natural or artificial, influencing these bodies. Consequently, the integration of interstellar object studies with traditional SETI methodologies could provide a complementary detection strategy, sensitive to both natural anomalies and engineered phenomena. In practical terms, pursuing this expanded framework demands unprecedented coordination among observatories, space agencies, and research institutions. Data must be shared globally, observations synchronized, and analytical models applied consistently. Only through such collaboration can researchers capitalize on the fleeting presence of interstellar visitors to extract maximal scientific and potentially technological information. 3I Atlas, therefore, becomes a focal point not merely for planetary science or cometary physics, but for the broader enterprise of cosmic exploration, exemplifying how anomalous objects can challenge and expand the boundaries of human knowledge and the search for intelligence beyond Earth. October 30th, 2025 marks a pivotal moment in the observational campaign of 3I Atlas, the object's perihelion passage, its closest approach to the Sun at approximately 1.4 astronomical units. This passage represents the culmination of months of meticulous tracking, chemical analysis, and modeling a final, fleeting window to gather high-fidelity data before the interstellar visitor recedes into the cosmic expanse. As the object swings around the Sun, different surface regions receive peak solar flux, potentially activating previously dormant vents and altering the outgassing patterns that have already confounded predictions. The precision of this encounter underscores the urgency. Every observation is precious, and the alignment of terrestrial and space-based instruments must be orchestrated to capture the full spectrum of dynamical and chemical behavior. The changing geometry between Earth, 3I Atlas, and the Sun alters observational conditions continuously. From different vantage points, plumes and tail structures appear in new configurations, revealing subtle aspects of rotation, surface heterogeneity, and particle ejection dynamics. Mars offers a unique perspective during early October, with orbiters such as the Mars Reconnaissance Orbiter, MAVEN, and Mars Express poised to provide complementary views impossible from Earth alone. The combination of terrestrial telescopes and orbital platforms creates a multi-dimensional dataset, allowing scientists to probe shape, rotation, state, and activity patterns in unprecedented detail. These observations, carefully coordinated and timed, could illuminate the mechanisms by which 3I Atlas maintains apparent dynamical stability despite vigorous outgassing. Crucially, the Perihelion approach offers the best chance to resolve the natural versus artificial debate. If non-gravitational acceleration remains undetectable despite intensified solar heating and increased activity, it strengthens the anomaly narrative and suggests either extraordinary natural mechanisms such as symmetric venting or extreme mass, or a level of engineered stabilization that mimics natural processes. Conversely, detection of subtle but consistent acceleration corresponding to measured outgassing would provide compelling evidence that conventional physics fully explains the dynamics, affirming natural origins. Achieving this precision requires careful error analysis, repeated measurements across independent instruments, and the integration of astrometry, photometry, and spectroscopy into coherent models. Beyond the scientific measurements, Perihelion highlights operational and logistical challenges. Telescope schedules must accommodate rapid repositioning and extended exposures, while spacecraft observations require precise trajectory calculations and instrument calibration. Even minor deviations in predicted position could compromise data quality, emphasizing the narrow margin for error inherent in studying transient interstellar visitors. The campaign exemplifies the intersection of human coordination, technological capability, and cosmic timing, where every second of observation holds potential insights into both physics and the deeper questions of interstellar material origins. In this climactic observational phase, 3I Atlas serves as a natural laboratory for testing the limits of cometary physics, interstellar dynamics, and potentially artificial intervention. Its perihelion passage concentrates months of anticipation into a narrow window, demanding the full capabilities of contemporary astronomy. As scientists prepare to capture every nuance of activity, composition, and motion, the object challenges assumptions and expectations, presenting a rare opportunity to confront the interface between the natural and the extraordinary. The Perihelion approach thus embodies both culmination and potential revelation, a temporal and spatial convergence that may finally yield clarity on one of the most enigmatic objects humanity has ever observed. The Vera C. Rubin Observatory heralds a transformative era in the study of dynamic celestial phenomena, and for interstellar visitors like 3I Atlas, it represents a quantum leap in observational capability. Located atop Cerro Pachon in Chile, the observatory's Wide-Field Survey, the Legacy Survey of Space and Time, LSST, will capture the entire southern sky every 3 nights to unprecedented depth, creating a decade-long cinematic record of cosmic evolution. For interstellar object detection, this systematic cadence transforms chance discoveries into statistically robust observations, dramatically increasing the likelihood of capturing transient anomalies. Where previous surveys Atlas, Pan-STARRS, Catalina Sky Survey relied on serendipity and incremental coverage, Rubin offers a continuous, high-resolution time-lapse of the dynamic cosmos, enabling detection, tracking, and characterization of fleeting visitors with unparalleled precision. Current interstellar object detection remains limited by both sensitivity and temporal coverage. Even with the combined efforts of multiple surveys, the faintest and fastest-moving visitors may elude detection, providing only partial glimpses and sparse data points. Rubin's combination of deep limiting magnitudes, rapid cadence, and wide-field imaging addresses these limitations, permitting early identification months or even years before perihelion passage. This extended lead time facilitates comprehensive follow-up observations, including high-resolution spectroscopy, astrometric refinement, and detailed photometric monitoring, allowing astronomers to construct complete temporal profiles of activity, rotation, and chemical evolution. For 3I Atlas, Rubin-like capabilities could have offered continuous monitoring of plume evolution, tail development, and subtle variations in coma structure, providing critical insight into both natural dynamics and potential anomalies. The increased detection rate promised by Rubin has profound implications for understanding interstellar visitors as a population. Whereas today, only 3 confirmed objects have been catalogued over a decade, Rubin is expected to identify dozens annually once fully operational. Such a dataset would allow astronomers to distinguish between rare outliers and systematic patterns, identifying objects that adhere to predictable cometary physics versus those exhibiting anomalous behavior. Statistical analysis across a larger sample could reveal whether CO₂-dominated outgassing, nickel-rich chemical signatures, or suppressed non-gravitational acceleration are truly exceptional or indicative of broader phenomena in interstellar material. This capability not only refines the understanding of 3I Atlas, but also contextualizes it within the broader framework of interstellar object behavior. From a SETI perspective, Rubin-era detection transforms the investigative paradigm. With rapid identification of interstellar visitors, astronomers can apply immediate spectroscopic and astrometric analysis to assess natural versus artificial signatures, expanding the search for extraterrestrial intelligence beyond traditional radio or optical signals. Objects displaying improbable dynamics, anomalous chemistry, or potential evidence of trajectory stabilization could be flagged in real time, enabling targeted observation campaigns and, in extreme cases, mission planning for direct rendezvous or in situ analysis. The combination of systematic detection, comprehensive follow-up, and statistical validation positions the Rubin Observatory as a cornerstone in the next generation of cosmic reconnaissance, where interstellar anomalies like 31ATLAS become not isolated curiosities but integral components of a broader investigative framework. In summary, the Vera Rubin era exemplifies the confluence of observational sophistication, statistical rigor, and strategic foresight. For 3I Atlas, it promises the possibility of extended monitoring, high-fidelity analysis, and deeper understanding of both its chemical and dynamical properties. Beyond this single object, Rubin offers the prospect of transforming the study of interstellar visitors into a mature, population-level science, capable of revealing the full spectrum of natural variability and, potentially, the subtle signatures of intelligence embedded in the silent travelers of the cosmos. After months of intensive observation and meticulous analysis, the central question crystallizes: what is 3I Atlas? The evidence amassed from Hubble, Webb, Gemini South, and other observatories presents a complex portrait, one that resists simple classification. Chemically, the object is dominated by CO₂ outgassing, with unusually high ratios compared to water and carbon monoxide, suggesting formation near a carbon dioxide ice line in a distant stellar system. Dynamically, it exhibits vigorous outgassing without measurable non-gravitational acceleration, defying the expectations of centuries of cometary physics. Morphologically, it displays evolving plumes and tail structures, transitioning from anti-tail illusions to conventional dust streams, indicative of both rotation and surface heterogeneity. Each feature, while individually explainable, combines into a constellation of anomalies that challenge conventional interpretation. Mainstream interpretations, grounded in naturalistic frameworks, propose that 3I Atlas is an interstellar comet exhibiting extreme yet plausible properties. Its apparent stability could be a consequence of either an anomalously massive nucleus, absorbing momentum without measurable deflection, or a precise symmetry in outgassing that cancels net thrust. The chemical peculiarities, including the nickel without iron signature, might arise from space weathering, selective sublimation, or formation under conditions not represented in the solar system. From this perspective, 3I Atlas exemplifies the diversity of interstellar objects, reflecting formation and evolutionary processes that are rare but natural. Conversely, speculative interpretations consider the possibility of artificial origin. The precise balance of activity and trajectory stability, coupled with unusual chemical signatures, mirrors principles used in spacecraft engineering. Cold gas microthrusters or reaction control systems could, in theory, maintain a stable path while allowing controlled venting for reconnaissance purposes. The nickel emission, while potentially natural, resembles erosion patterns from high-temperature superalloys, raising questions about whether the object might be a technologically constructed probe. Its apparent mass concentration could reflect intentional design for long-duration interstellar transit rather than natural aggregation. Even its trajectory hints at deliberate orientation, optimizing solar exposure and observation opportunities. The tension between natural and artificial explanations underscores the difficulty of interpretation. Extraordinary claims demand extraordinary evidence, and while 3I Atlas exhibits anomalies that invite speculation, the current data falls short of definitive proof. Each unusual characteristic remains compatible with natural processes, provided they occur under rare or finely tuned conditions. At the same time, the object challenges theoretical frameworks developed from solar system comets, illustrating that interstellar visitors may obey rules or constraints unfamiliar to us. In this sense, 3I Atlas occupies a liminal space between cosmic oddity and potential artifact, a frontier that stretches both observational capability and imagination. Ultimately, this phase of analysis reveals the dual nature of scientific inquiry at the frontier. Data-driven observation must coexist with thoughtful speculation. While mainstream science emphasizes parsimonious, natural explanations, the anomalies of 3I Atlas encourage open-minded consideration of alternative possibilities. The object becomes a lens through which we examine not only the mechanics of cometary physics, but the boundaries of knowledge itself. It embodies the delicate interplay between measurable phenomena and the hypotheses they inspire, prompting reflection on the limitations of empirical certainty when confronted with the extraordinary. The role of carbon dioxide in shaping the behavior of 3I Atlas cannot be overstated. CO₂, with its lower sublimation temperature relative to water ice, dominates the comet's activity at distances where H2O remains largely inert. This chemical property offers a potential explanation for the object's isotropic venting and apparent dynamical stability. Unlike typical comets, where water-driven jets produce directional thrust, CO₂ sublimation from multiple, evenly distributed vents across the surface may generate outgassing forces that counterbalance each other. Such a mechanism, though improbable, aligns with the observed absence of non-gravitational acceleration, suggesting that chemical composition is a key factor in maintaining the object's enigmatic trajectory. Spectroscopy from the Webb Space Telescope provides detailed insights into this process. Infrared measurements reveal the strength and distribution of CO₂ emission lines, which vary subtly with rotation and solar illumination. The observed flux patterns indicate that sublimation is not confined to a single active region, but occurs across a wide portion of the nucleus. This distributed activity creates a quasi-symmetrical force profile, minimizing net momentum transfer and explaining why the expected orbital deviations remain below detection thresholds. Simultaneously, the minor presence of water and carbon monoxide contributes to transient local accelerations, producing ephemeral but insufficient forces to alter the overall trajectory significantly. The interplay of chemical composition and rotational dynamics further complicates the picture. 3I Atlas exhibits a slow, complex rotation as inferred from periodic variations in brightness and coma morphology. This rotation redistributes the orientation of active vents relative to the Sun, effectively averaging out directional thrust over each rotation cycle. The combination of isotropic CO₂-driven outgassing and rotational averaging creates a natural stabilization mechanism, one that could account for the persistent inertial behavior despite observable activity. In essence, the comet behaves as a self-regulating system, where the forces of sublimation are balanced by geometry and spin, producing an extraordinary equilibrium that mimics artificial control. Moreover, the CO₂ dominance raises questions about the object's origin. Comets formed in the outer regions of planetary systems, beyond the H2O snowline, can accumulate substantial CO₂ ice, yet the ratios observed in 3I Atlas suggest formation in an environment distinct from the typical solar system profile. Such a chemical fingerprint implies a birthplace with unique thermal and chemical conditions, potentially a young system with volatile-rich outer regions. The exotic composition, combined with the suppressed acceleration, highlights the convergence of chemistry, physics, and orbital mechanics in producing a natural yet anomalous interstellar visitor. Ultimately, the chemical analysis illustrates the profound connection between microscopic properties and macroscopic behavior. The molecules sublimating from 3I Atlas do not merely constitute an observational signature, they govern the very dynamics that challenge our understanding of motion. By emphasizing the role of CO₂ and the isotropy of outgassing, this phase of investigation bridges the gap between chemical and mechanical explanations, offering a pathway toward reconciling the observed activity with the enigmatic trajectory. The interstellar comet becomes both a laboratory and a puzzle, demonstrating that even subtle chemical differences can generate cosmic phenomena that stretch the imagination and redefine the boundaries of plausible physics. Estimating the mass of 3I, Atlas provides critical insight into why its trajectory appears immune to the forces of outgassing. Classical cometary physics dictates that smaller bodies possessing relatively low mass are highly sensitive to the momentum imparted by sublimating gases. For 3I Atlas, however, preliminary analyses suggest a nucleus of substantial density, with mass estimates approaching that of a small mountain compressed into the form of a cometary nucleus. This enormous inertia could inherently suppress the observable effects of outgassing, rendering otherwise measurable non-gravitational acceleration effectively undetectable. In essence, the mass acts as a buffer, a stabilizing anchor amidst vigorous activity, preserving the hyperbolic trajectory that defines its interstellar journey. Calculating the mass involves integrating multiple observational datasets. Photometry provides estimates of the nucleus size, while spectroscopy informs the volatile content and production rates of sublimating gases. Combining these parameters with observed velocities of escaping molecules enables the computation of expected recoil forces. When compared to the negligible orbital deviations recorded through astrometry, the inferred mass must be sufficiently large to absorb the cumulative momentum from these outgassing events without producing detectable acceleration. The calculations reveal a finely balanced system where size, density, and vent distribution converge to produce an appearance of inertial stasis despite ongoing energetic processes. The mass argument also informs models of rotational stability. A substantial nucleus, combined with a slow or complex rotation, can facilitate quasi-isotropic venting over time. The rotational period ensures that no single vent dominates the cumulative thrust, further suppressing non-gravitational effects. Observed brightness variations, indicative of spin and surface heterogeneity, align with this hypothesis, suggesting that both mass and rotational dynamics collaborate to maintain an anomalously stable trajectory. Even minor asymmetries in venting are averaged out over multiple rotations, producing an elegant equilibrium that defies intuitive expectations, yet remains physically plausible. Comparisons to other interstellar objects provide additional context. Oumuamua, though smaller and less massive, displayed acceleration without visible outgassing, hinting at sublimation of highly volatile ices or alternative mechanisms. Borisov, by contrast, exhibited conventional cometary behavior, where mass and venting dynamics produced expected non-gravitational acceleration. 3I Atlas occupies a unique position along this continuum, combining substantial mass with vigorous CO₂-driven activity to create a paradoxical balance: active yet inert, energetic yet dynamically stable. Its mass is both the key to understanding this behavior and a source of enduring intrigue, suggesting that interstellar objects may inhabit regimes of physics and chemistry not represented in the solar system. Finally, the mass argument intersects with broader implications for interstellar dynamics. A dense CO₂-rich nucleus, traveling on a hyperbolic trajectory, challenges assumptions about the composition and physical limits of such objects. It compels reconsideration of models predicting the frequency, detectability, and behavior of interstellar visitors. In the delicate interplay between mass, chemical activity, and rotational state, 3I Atlas demonstrates that even slight variations in physical parameters can produce outcomes that confound expectations, offering both a challenge to theory and an invitation to expand the horizons of observational astrophysics. Lessons from Oumuamua provide a vital historical context for interpreting 3I Atlas, underscoring the challenges inherent in studying interstellar visitors. Discovered in October 2017 by the Pan-STARRS telescope, Umuamua captivated astronomers with its hyperbolic trajectory, unusual elongated shape, and the unexpected non-gravitational acceleration detected without visible outgassing. Initially classified as an asteroid due to its lack of observable cometary activity, it soon defied expectations, exhibiting acceleration that suggested sublimation of highly volatile compounds, possibly hydrogen ice, or alternative mechanisms such as radiation pressure. The object became a touchstone for discussions of natural versus artificial explanations, highlighting the difficulty of distinguishing between extraordinary physical phenomena and potential engineering. The comparison between Umuamua and 3I Atlas illuminates a key distinction. Whereas Umuamua accelerated without measurable activity, 3I Atlas displays vigorous, chemically traceable outgassing without corresponding acceleration. This inversion of anomaly types underscores the diversity of interstellar object behavior and the limits of our existing models. Both objects challenge the predictive frameworks derived from solar system comet observations, but in complementary ways. Oumuamua emphasized the possibility of undetected mechanisms for propulsion, whereas 3I Atlas emphasizes the potential for symmetry, mass, and rotational averaging to mask expected effects. Together, they suggest that interstellar objects may inhabit extreme regimes of physical behavior, with properties and dynamics rarely represented in familiar celestial populations. Analyzing Oumuamua also informs observational strategy. Its brief visibility and rapid departure from the solar system highlighted the importance of rapid detection and immediate follow-up. In that instance, despite global coordination, the dataset remained sparse, leaving fundamental questions unresolved. 3I Atlas benefits from this precedent. Astronomers have applied lessons learned to ensure comprehensive, multi-instrument monitoring, combining high-resolution imaging, spectroscopy, and photometry to capture the object's trajectory, activity, and chemical signatures with maximal fidelity. The historical context underscores the critical need for real-time collaboration, meticulous calibration, and rapid data analysis in the study of transient interstellar phenomena. Furthermore, Umuamua catalyzed discourse regarding the possibility of artificial origin for interstellar objects. Though the prevailing consensus favored natural explanations, its extreme elongation, unusual light curve, and unexplained acceleration prompted careful consideration of engineered alternatives. This precedent legitimizes, within scientific discourse, the exploration of similar hypotheses for 318 LAS, where improbable venting symmetry, unexpected chemical signatures, and dynamical stability invite comparable questions. By situating 3I Atlas within the continuum of observed anomalies, researchers gain a framework for evaluating both natural mechanisms and speculative interventions without violating the standards of empirical investigation. Ultimately, the lessons from Umuamua are not merely historical, they are methodological and conceptual. They demonstrate that interstellar visitors may defy intuitive expectations, challenge models calibrated on solar system bodies, and demand adaptive scientific thinking. For 3I Atlas, Umuamua provides both a cautionary tale and a roadmap, a reminder that the universe presents anomalies with subtle signatures, that careful observation can reveal profound mysteries, and that the boundary between natural and artificial interpretations may be both delicate and consequential. By reflecting on past encounters, astronomers position themselves to extract maximum insight from this new, enigmatic visitor. The lessons from 2Y Borisov, discovered in August 2019, complement those drawn from Umuamua, providing a contrasting template for interstellar comet behavior. Unlike its predecessor, Borisov exhibited a trajectory and activity entirely consistent with known cometary physics. Its outgassing, dominated by water, ice, and modest CO emissions, generated measurable non-gravitational acceleration as predicted by standard models. Morphologically, it displayed a typical coma and tail, responding predictably to solar radiation and gravitational influences. Borisov thus represented the baseline for interstellar comet behavior, a reference against which the anomalies of both Umuamua and 3I Atlas could be compared. For 3I Atlas, Borisov's predictability highlights the extraordinary nature of its behavior. Where Borisov's dynamics aligned precisely with expectations, 3I Atlas's vigorous CO₂ outgassing produces no detectable acceleration, creating a counterpoint that emphasizes the divergence from conventional models. By examining the factors that contributed to Borisov's standard behavior, nucleus mass, rotation, vent distribution, and chemical composition, astronomers can identify which variables are potentially responsible for 3I Atlas's anomalous stability. In doing so, they isolate the interplay between mass, isotropic venting, and rotational dynamics as a plausible natural explanation for suppressed momentum transfer, while also recognizing that the object occupies an extreme edge of parameter space, rarely encountered in interstellar populations. Comparative studies also refine observational expectations. Borisov's outgassing produced clear spectroscopic signatures that correlated with measured accelerations, enabling validation of theoretical models for volatile sublimation, mass loss rates, and non-gravitational effects. In contrast, 3I Atlas presents an observational paradox: measurable emissions without correlating acceleration, challenging the assumptions embedded in those models. By juxtaposing the two cases, scientists can better constrain the limits of natural mechanisms, quantify the improbability of perfect vent symmetry, and explore alternative explanations, including subtle artificial stabilization or previously unrecognized natural processes. The contrast clarifies what is expected versus what is anomalous, sharpening the interpretive lens. Furthermore, Borisov's chemical profile provides a baseline for assessing the origins of interstellar objects. Its composition reflected formation in a cold, distant region of a protoplanetary disk, dominated by water, ice, and typical trace volatiles. 380LAS, by contrast, exhibits a CO₂-rich composition and unusual nickel signatures, hinting at a distinct birthplace or evolutionary history. Comparing these signatures allows astronomers to explore how chemical environment influences both activity and dynamics, suggesting that formation conditions may predispose certain objects to anomalous behavior. The juxtaposition with Borisov emphasizes that the universe produces both predictable interstellar comets and rare, extreme outliers, each offering different insights into stellar system formation and interstellar material transport. Ultimately, Borisov reinforces the notion that 3I Atlas occupies a unique niche in interstellar object studies, where Oumuamua challenged expectations through invisible acceleration and Borisov validated conventional models. 3I Atlas inverts the pattern, active but dynamically inert. The contrast sharpens the mystery, highlights the range of natural possibilities, and focuses attention on the precise combination of mass, chemical composition, vent symmetry, and rotational dynamics that may explain the anomaly. Through this comparative framework, the object is situated not as an isolated curiosity, but as part of a broader continuum of interstellar phenomena, illuminating both the diversity and the enigmatic potential of matter traveling between stars. To further contextualize 3I Atlas, astronomers turn to other well-studied comets within the solar system, using them as benchmarks to understand expected behavior under similar conditions. Missions like Rosetta, which studied 67P Churyumov-Gerasimenko in exquisite detail, provided invaluable insights into cometary nuclear structure, surface heterogeneity, and venting dynamics. Observations of Hale-Bopp and Halley revealed how nucleus rotation, vent orientation, and chemical composition interact to produce predictable outgassing patterns and measurable non-gravitational acceleration. By comparing these solar system exemplars with 3I Atlas, researchers establish the boundaries of natural behavior, isolating anomalies and highlighting features that defy conventional explanation. Rosetta's mission, in particular, demonstrates how distributed venting and rotation can moderate the net effect of outgassing on trajectory. The nucleus of 67P exhibited multiple active regions that were not perfectly aligned, yet even small asymmetries produced detectable accelerations measurable by Doppler tracking and orbit reconstruction. Scaling these insights to 3I Atlas, with its substantially larger mass and CO₂-dominated activity, suggests that isotropic or near-symmetric venting, combined with rotation, could plausibly suppress measurable non-gravitational effects. Nevertheless, achieving the observed stability requires a degree of symmetry and mass distribution that is extraordinarily precise, stretching the limits of naturally occurring scenarios. Observations of Hale-Bopp and Halley further emphasize the predictability of solar system comets. Both displayed dynamic, visually striking tails and comas that responded directly to solar radiation and orbital mechanics, producing measurable deviations consistent with calculated outgassing forces. These cases provide a critical contrast. The physics governing well-understood comets reliably produce observable orbital perturbations, reinforcing the exceptional nature of 3I Atlas's inertial stability. By establishing the expected range of behaviors, astronomers can quantify the degree to which 3I Atlas diverges from normative cometary dynamics, lending statistical weight to the anomaly and guiding theoretical modeling. These benchmarks also aid in interpreting chemical signatures. In 67P and Hale-Bopp, water ice dominates outgassing, with minor contributions from CO, CO₂, and other volatiles. The contrast with 3I Atlas's CO₂-rich composition underscores the influence of chemical environment on venting dynamics. Carbon dioxide sublimates more evenly across illuminated surfaces at distances where water remains largely inactive, potentially producing quasi-isotropic thrust. This chemical distinction, when considered alongside mass and rotational state, contributes to a natural explanation for the suppressed acceleration while highlighting the uniqueness of the interstellar object relative to familiar solar system comets. Ultimately, these benchmarks serve as both a foundation and a foil. By analyzing well-characterized comets, astronomers delineate the physical and chemical parameters that govern outgassing, tail morphology, and orbital deviation. Against this backdrop, 3I Atlas stands out as an object whose combination of mass, chemical composition, vent geometry, and rotation produces behavior at the extreme edge of plausibility. The contrast sharpens both the scientific and philosophical dimensions of the mystery, situating the interstellar visitor within a continuum of cometary phenomena, while emphasizing the extraordinary nature of its apparent defiance of expected physics. A critical factor in the mystery of 3I Atlas is the geometry and distribution of its venting regions. Cometary jets are rarely uniform. Even within solar system comets, active vents produce localized thrusts that generate measurable changes in trajectory. For 3I Atlas, observational data suggest that active vents are arranged with remarkable symmetry, an improbable configuration that could suppress the net effect of outgassing. High-resolution imaging of the coma and periodic variations in photometric brightness imply a rotation state that distributes venting forces evenly over time. This combination of geometry and spin creates a natural counterbalance, effectively neutralizing the momentum transfer that would otherwise result in detectable non-gravitational acceleration. Analyzing vent symmetry involves integrating multiple datasets: tail morphology from Gemini South, coma structure from Hubble, and spectral line intensities from Webb. Variations in plume, brightness, and orientation provide indirect measurements of vent locations on the nucleus, while rotation-induced periodicities in these features inform models of temporal averaging. Simulations incorporating these parameters demonstrate that, with near-perfect vent alignment, even substantial outgassing can produce minimal net thrust. This insight represents a critical step toward reconciling the paradox of observable activity and trajectory stability, suggesting that physical processes alone may suffice to explain the anomaly, albeit under extraordinary circumstances. The rotational state of 318 LAS is equally significant. Slow, complex rotation ensures that vents are alternately exposed to solar radiation, distributing thrust vectors across the nucleus over time. This rotational averaging can reduce the net force along any given axis, producing a dynamic equilibrium that mimics artificial stabilization. Observed variations in brightness, correlated with rotation, provide evidence for this mechanism, confirming that both vent symmetry and rotation contribute to the observed inertial behavior. Without these factors, even massive CO₂-driven outgassing would result in detectable acceleration, making their alignment crucial to understanding the phenomenon. This analysis also invites reflection on natural improbability versus artificial design. While such precise vent symmetry and rotational averaging could theoretically arise through natural processes, the statistical likelihood is extremely low. Some researchers have proposed that subtle artificial mechanisms, intentionally or unintentionally integrated, could enhance stability, though no direct evidence currently supports this hypothesis. The object's composition, including unusual nickel enrichment, further complicates the discussion, as it could either reflect rare natural formation conditions or engineered material properties. Regardless of interpretation, the interplay between vent geometry, rotation, and mass emerges as the principal driver of 318 LAS's apparent defiance of Newtonian expectations. In conclusion, understanding the geometry and venting of 3I Atlas illuminates one of the most critical mechanisms by which the object maintains its extraordinary stability. Through a delicate balance of symmetry, rotation, and chemical activity, the nucleus effectively neutralizes the forces of its own emissions. This realization bridges observation and theory, demonstrating that even the most improbable natural configurations can generate behavior that appears paradoxical. The object's vent geometry thus serves as both a key explanatory factor and a window into the delicate choreography that governs its motion through interstellar space. Speculative considerations extend the discussion beyond natural explanations, introducing the possibility of artificial control or engineering. While 3I Atlas's behavior can be modeled through extreme yet plausible natural mechanisms, massive CO₂, rich nucleus, precise vent symmetry, and rotational averaging, the extraordinary precision required to suppress non-gravitational acceleration raises questions that invite alternative hypotheses. One possibility is that the object represents a technological artifact, a probe or vehicle engineered to traverse interstellar distances while maintaining a stable trajectory. In this scenario, mechanisms analogous to spacecraft reaction control systems could maintain orientation, compensate for outgassing, and regulate spin, producing the apparent inertial stasis observed from Earth. Such an artificial control hypothesis relies on principles familiar in human engineering. Cold gas microthrusters, for example, can impart minute corrections to trajectory without producing detectable macroscopic motion. Momentum wheels or gyroscopic stabilizers can adjust orientation with high precision, ensuring symmetric exposure of active surfaces to solar radiation or other environmental factors. Applied on the scale of an interstellar object, these mechanisms could theoretically neutralize the effects of venting while allowing sublimation to continue for observation or energy management. The challenge lies in scale and energy. Maintaining such a system across vast distances and time spans implies either extraordinary engineering or a degree of natural luck in vent distribution, highlighting the borderline between speculative design and improbable natural alignment. Observationally, evidence for artificial stabilization remains circumstantial. The precise alignment of venting and the suppression of expected acceleration are consistent with engineering, but not exclusive to it. Alternative natural explanations, distribution of mass, rotational dynamics, isotropic CO₂ venting, could achieve similar outcomes under highly specific conditions. Nonetheless, the artificial hypothesis provides a coherent framework to interpret features that are statistically improbable under naturalistic assumptions. This includes the combination of mass, chemical composition, vent symmetry, and dynamical stability, each element contributing to a pattern suggestive of intentional design. Philosophically, entertaining the possibility of artificial control shifts the discourse from pure astrophysics to considerations of technological and cognitive scales beyond human experience. If an advanced civilization were capable of deploying probes across interstellar distances with such subtlety, their engineering principles would necessarily exceed contemporary human understanding. 3I Atlas then becomes not merely an object to be measured, but a messenger of possibility, challenging assumptions about both the natural diversity of interstellar objects and the potential prevalence of intelligent activity across the galaxy. The speculation underscores the need for rigorous, multidisciplinary study, combining physics, chemistry, and astrometry with imaginative yet disciplined interpretation. Ultimately, the artificial control hypothesis exemplifies the tension at the frontier of knowledge. It is simultaneously improbable and compelling, grounded in engineering principles, yet unconfirmed by direct evidence. By framing 3I Atlas in this context, researchers maintain a balance between skepticism and curiosity, acknowledging both natural and engineered possibilities. Whether a cosmic coincidence or an artifact of intelligence, the object's extraordinary behavior continues to challenge, inspire, and expand the boundaries of human understanding of interstellar phenomena. The material signatures of 3I Atlas offer additional enigmatic clues to its origin and nature. Spectroscopic analysis indicates the presence of nickel without associated iron, a chemical anomaly rarely observed in natural cometary bodies. In conventional stellar and planetary formation, nickel and iron typically co-condense in similar proportions, reflecting nucleosynthetic processes in supernova remnants. The apparent isolation of nickel challenges these expectations, prompting consideration of both unusual natural processes and potential artificial analogues. Some natural scenarios include selective sublimation, space weathering, or formation under unique conditions in an exotic protoplanetary disk. Each hypothesis carries a low probability, yet remains physically plausible, illustrating the delicate interplay between observation and inference. The nickel signature also invites parallels to engineered materials. High-temperature superalloys, used in human aerospace engineering, exhibit compositions enriched in nickel relative to iron to achieve desirable mechanical properties under extreme conditions. While it would be speculative to assert artificial origin solely on this basis, the chemical similarity underscores the broader anomaly. The composition, in combination with CO₂ dominance and dynamic stability, forms a suite of unusual traits collectively improbable in naturally occurring objects. This convergence amplifies the mystery, highlighting the limits of conventional formation models and prompting interdisciplinary examination, integrating material science, astrophysics, and chemical kinetics. Beyond elemental composition, the observed materials influence dynamical behavior. Nickel-rich surfaces may have different thermal properties, sublimation thresholds, and structural rigidity compared to traditional cometary ice rock mixtures. These factors affect outgassing symmetry, vent longevity, and response to solar irradiation. In 3.1, ATLAS. Such material properties could reinforce the quasi-isotropic outgassing necessary to suppress non-gravitational acceleration, creating a feedback loop where chemical composition and mechanical behavior are mutually reinforcing. The result is an object whose internal and external characteristics conspire to produce extraordinary stability while maintaining observable activity. This phase of analysis exemplifies the integration of chemical, physical, and dynamical data. By examining material signatures in concert with vent geometry, rotational state, and mass estimates, astronomers build a comprehensive model of the object's behavior. The unusual nickel enrichment, when combined with CO₂-dominated outgassing and rotational averaging, offers a plausible pathway for the observed inertial stability, yet the improbability of such precise alignment continues to fuel both naturalistic and speculative hypotheses. 3I Atlas thus occupies a space where chemistry, physics, and potential engineering converge, creating a multidimensional enigma that challenges the boundaries of observational astrophysics and material science alike. Trajectory patterns of 3I Atlas provide one of the most compelling lenses through which to examine the object's anomalous behavior. High-precision astrometry, combining data from Hubble, Webb, Gemini South, and other observatories, has traced the interstellar visitor's hyperbolic path with unprecedented accuracy. The object's inbound trajectory, approaching from the direction of Sagittarius, aligns with predictions for an interstellar origin, while its perihelion passage occurs at a comfortable distance from Earth, minimizing observational interference. Yet, despite the object's activity and observable venting, its path remains remarkably linear and stable, a motion that adheres closely to gravitational expectations alone. The absence of measurable non-gravitational acceleration underscores the mystery and invites deeper analysis of trajectory patterns as potential evidence of either natural extremity or deliberate stabilization. Small deviations in motion, or lack thereof, can offer clues about the underlying forces at play. For 3I Atlas, computational models incorporating mass, vent symmetry, rotational dynamics, and sublimation rates indicate that the observed trajectory could result from a finely balanced natural configuration. However, the degree of precision required stretches credulity. Any minor asymmetry in vent distribution or rotation could produce detectable acceleration. The persistent stability thus raises the possibility that additional mechanisms, either natural, such as internal mass distribution anomalies, or artificial, such as subtle control systems, may be influencing motion. The trajectory, therefore, becomes both a diagnostic tool and a narrative element, revealing the delicate balance between forces that defines the object's behavior. Analyses of past interstellar visitors provide context for interpreting these patterns. Oumuamua, for example, exhibited acceleration without visible outgassing, suggesting alternative propulsion or unobserved volatile release, while Borisov behaved predictably, validating classical cometary models. 3I Atlas, in contrast, demonstrates activity without acceleration, inverting the anomaly observed in Umuamua. Comparing these cases highlights the diversity of interstellar object dynamics and situates 3I Atlas as a unique specimen, whose trajectory offers both a puzzle and an opportunity to probe the interplay between natural physics and potential artificial factors. Trajectory analysis also informs observational strategy. By predicting precise positions and velocities, astronomers can optimize telescope pointing, schedule spectroscopic observations, and coordinate space-based instruments, including Mars orbiters, to capture complementary perspectives. The accuracy of trajectory modeling enhances the ability to correlate venting activity with rotational orientation, chemical composition, and potential deviations, providing a multidimensional understanding of the object. In essence, trajectory patterns serve not only as a measurement of motion, but as a narrative thread connecting observational data, theoretical modeling, and the deeper mystery of 3I atlas's origin and behavior. Ultimately, the trajectory is both a canvas and a clue. Its remarkable linearity amid observable activity embodies the central paradox of 3I atlas, compelling scientists to explore the interplay of mass, vent symmetry, rotation, and possibly artificial stabilization. As a record of interstellar passage, the path tells a story of precision, improbability, and cosmic intrigue, anchoring the object's narrative within the larger framework of celestial mechanics, while simultaneously challenging its boundaries. Evidence standards and scientific skepticism form the backbone of interpreting anomalies like 3I atlas. In astrophysics, extraordinary claims require rigorous verification through multiple independent observations, robust statistical analysis, and cross-validation across instruments and methodologies. The combination of unusual venting behavior, anomalous chemical composition, and suppressed non-gravitational acceleration presents an extraordinary scenario, one that challenges existing models of cometary dynamics while demanding meticulous scrutiny. Scientists are compelled to maintain methodological rigor, ensuring that data quality, calibration, and error propagation are meticulously accounted for before entertaining explanations that stretch beyond conventional frameworks. The principle of convergence plays a critical role. No single observation, whether spectroscopic, photometric, or astrometric, suffices to substantiate extraordinary hypotheses. Only through the convergence of multiple, independently obtained datasets can confidence be established regarding the reality of anomalies. In the case of 3I atlas, Hubble imaging, Webb spectroscopy, Gemini South tail morphology, and precise astrometry collectively confirm the object's hyperbolic trajectory, CO₂-dominated outgassing, and apparent dynamical stability. Each line of evidence strengthens the anomaly while simultaneously constraining plausible explanations, highlighting the dual role of evidence. It elucidates patterns while simultaneously raising questions about underlying mechanisms. Skepticism serves as both a safeguard and a catalyst for discovery. Researchers must account for potential confounding factors, instrumental artifacts, observational bias, projection effects, and modeling assumptions before considering hypotheses that invoke artificial control or extreme natural circumstances. At the same time, rigorous skepticism does not preclude imaginative interpretation. Rather, it frames speculation within disciplined inquiry. By maintaining this balance, the scientific community ensures that conclusions are neither prematurely sensationalized nor dismissively conservative, preserving credibility while exploring the outer bounds of plausibility. Statistical reasoning further informs evaluation of anomalies. The combination of chemical peculiarities, vent symmetry, rotational dynamics, and trajectory stability constitutes a rare configuration. Quantifying the probability of such alignment occurring naturally provides context for interpreting potential artificial scenarios. Even if the likelihood is low, it must be weighed against the capacity of natural processes to produce rare but physically consistent outcomes. This probabilistic framework allows scientists to rank competing hypotheses, guiding observational priorities and informing the allocation of resources for follow-up studies. In this phase, evidence standards shape both methodology and interpretation. The scrutiny applied to 3I atlas exemplifies the scientific method at its most exacting. Each dataset is evaluated for reliability, each anomaly quantified, and every hypothesis tested against converging lines of proof. By adhering to these standards, researchers navigate the tension between empirical rigor and speculative openness, ensuring that the extraordinary nature of 3.1 Atlas is neither overstated nor ignored. This disciplined approach lays the groundwork for deeper inquiry into the object's origins, composition, and dynamics, anchoring philosophical reflection in the solid foundation of scientific credibility. Spectral analysis and long-term stability measurements provide critical insight into the enduring mysteries of 3.1 Atlas. Repeated observations using the James Webb Space Telescope and high-resolution ground-based spectrographs confirm the persistence of CO₂-dominated outgassing over months, with periodic fluctuations corresponding to rotational phases. The spectrum shows not only the intensity of emitted gases, but also subtle shifts indicative of vent activity, thermal processing, and potential surface heterogeneity. These findings reveal a dynamic, yet controlled system. The comet remains chemically active while exhibiting an apparent suppression of net momentum transfer, a balance that persists over time and defies conventional expectations for bodies of similar composition and size. The temporal evolution of these chemical signatures offers further nuance. During the approach to perihelion, the intensity of CO₂ emission increases, yet the corresponding non-gravitational acceleration remains undetectable within observational limits. Minor contributions from water and carbon monoxide produce localized effects, but the overall trajectory remains remarkably stable. Analysis of emission line profiles indicates that the gas is released over a broad surface area rather than concentrated jets, reinforcing the hypothesis of quasi-isotropic venting. This temporal persistence suggests that the anomalous behavior is not a transient phenomenon, but an intrinsic property of the nucleus, maintained across rotational cycles and variable solar illumination. Coupling spectral data with rotational modeling provides a multidimensional perspective. The observed light curve variations, when analyzed alongside the distribution of vent activity, confirm a slow, complex rotation that averages out directional thrust over time. This rotational averaging, combined with isotropic CO₂-driven outgassing, offers a physically plausible mechanism for the object's apparent inertial stability. Computational simulations incorporating mass estimates, vent distribution, and rotational dynamics reproduce the observed trajectory within measurement uncertainties, demonstrating that natural processes, though improbable in their precision, can account for the anomaly without invoking artificial control. Nevertheless, the persistence of stability across multiple observational campaigns maintains the object's enigmatic character. Each dataset reinforces the paradox. Vigorous, measurable activity coexists with apparent dynamical inertia. The convergence of spectral, photometric, and astrometric evidence compels scientists to confront both the limits of current models and the potential for extreme natural configurations. The object's stability becomes a central constraint for theoretical interpretation, guiding the development of hypotheses that integrate chemical composition, rotational mechanics, and vent geometry into a coherent framework. Ultimately, spectral analysis and long-term monitoring demonstrate that 3.1 Atlas is a living laboratory of interstellar physics. Its sustained activity, persistent chemical signatures, and dynamic stability provide both data and paradox, challenging assumptions and offering a window into the complex interplay of mass, chemistry, and motion. By observing and quantifying these patterns over time, astronomers deepen their understanding of the mechanisms that could produce such extraordinary behavior, setting the stage for broader reflections on interstellar object diversity and the limits of physical predictability. The potential implications of 3.1 Atlas for the search for extraterrestrial intelligence, SETI, introduce a profound and speculative dimension to the investigation. Traditionally, SETI has focused on detecting electromagnetic signals, radio waves, laser pulses, or other forms of intentional communication emanating from distant civilizations. These methods assume that advanced life forms will broadcast detectable signatures across interstellar distances. However, 3I Atlas challenges this paradigm by suggesting that anomalous interstellar objects themselves may constitute evidence of intelligence, particularly if their behavior or composition appears deliberately controlled or optimized. A naturally rare configuration, such as precise vent symmetry combined with extreme chemical properties, could mimic or hint at engineering, prompting a re-evaluation of detection strategies beyond conventional signal-based approaches. The object's activity and stability provide a unique observational platform. Its hyperbolic trajectory ensures that it is unbound from the Sun, making it a genuine interstellar messenger, while CO₂-dominated outgassing offers measurable chemical signatures that persist over time. If an advanced civilization had engineered the object, the apparent suppression of non-gravitational acceleration could represent deliberate stabilization to facilitate observation or reconnaissance. The nickel-rich chemical signature, unusual for natural comets, further fuels speculation as it parallels properties found in high-temperature alloys used in human aerospace applications. While circumstantial, these factors invite rigorous interdisciplinary study, integrating astrophysics, materials science, and engineering analysis to evaluate the plausibility of artificial intervention. Beyond individual features, the context of interstellar object detection strengthens the SETI case. Only 3 confirmed interstellar visitors have been observed to date: Umuamua, Borisov, and now 3I Atlas. Within this limited dataset, 2 exhibit anomalous dynamics. Umuamua accelerated without detectable outgassing, while 3I Atlas outgasses without measurable acceleration. The rarity of these anomalies, coupled with their consistency across multiple observational platforms, raises questions about the natural frequency of such objects. Statistically, these deviations from expected behavior suggest either an unrecognized diversity in interstellar material or the influence of mechanisms that extend beyond conventional cometary physics. SETI frameworks must consider both possibilities, integrating anomaly analysis into the broader search for intelligence. Practical strategies emerge from this perspective. Future interstellar objects can be flagged for high-priority observation based on unusual trajectories, chemical signatures, or anomalous dynamical behavior. Multi-wavelength observations, combining optical, infrared, and spectroscopic data, allow for comprehensive characterization, enabling researchers to distinguish between extreme natural phenomena and potential engineered features. Coordinated global monitoring, rapid data sharing, and application of statistical models further enhance the capacity to evaluate objects like 3I Atlas. In doing so, the study of interstellar visitors evolves from purely astrophysical inquiry into a framework capable of detecting subtle markers of intelligence embedded in matter itself. Ultimately, 3I Atlas expands the conceptual landscape of SETI. It exemplifies how anomalies in chemical composition, activity, and trajectory can provide indirect evidence of engineering or deliberate design, even in the absence of intentional electromagnetic signaling. By situating the object within both natural and speculative contexts, astronomers and SETI researchers are compelled to develop flexible frameworks that integrate observational rigor with imaginative exploration. 3I Atlas thus becomes more than a comet. It is a bridge connecting empirical science, probabilistic reasoning, and the profound possibility that intelligence may leave signatures in ways previously unconsidered, challenging humanity to broaden its understanding of the cosmos and the methods by which we search for fellow travelers among the stars. Observational windows ahead present both opportunity and urgency in the study of 318LAS. As the object continues its journey past Perihelion and approaches a vantage point near Mars, a narrow interval arises for obtaining complementary observations from orbiting spacecraft. The Mars Reconnaissance Orbiter, MAVEN, and Mars Express are uniquely positioned to capture views unobstructed by Earth's atmosphere and free from terrestrial parallax, offering perspectives that can illuminate tail structure, vent orientation, and rotational state with unprecedented clarity. These observations, when integrated with Earth-based photometry, spectroscopy, and astrometry, create a multidimensional dataset capable of resolving subtle anomalies and refining models of vent symmetry and outgassing dynamics. Timing is critical. The alignment of 3-1 Atlas with Mars orbiters provides only brief windows in which instruments can achieve optimal resolution. Each exposure, each spectral scan, must be carefully scheduled, accounting for orbital mechanics, instrument sensitivity, and communication constraints. Failure to capture data within these intervals could result in a loss of unique information, particularly regarding transient phenomena such as plume variations, dust ejection, and rotational modulation of brightness. The fleeting nature of these windows emphasizes the need for coordinated international effort, rapid data processing, and adaptive observational strategies that respond to real-time developments in object behavior. These future observations also have the potential to constrain theoretical models. The vantage from Mars allows measurement of parallax-induced shifts in tail orientation, offering direct insight into particle ejection angles and velocities. Coupled with high-resolution imaging, these measurements can refine estimates of vent distribution, surface heterogeneity, and rotational axis orientation. By resolving these parameters, scientists can better evaluate the plausibility of natural explanations versus speculative artificial stabilization. The observational window thus becomes not merely a period of data collection but a critical test of competing hypotheses, bridging empirical evidence with theoretical interpretation. Moreover, the forward-looking observational strategy highlights the evolving interplay between technology and science. Coordinating spacecraft and ground-based telescopes across continents and planetary orbits represents a synthesis of human ingenuity, precision engineering, and cosmic opportunity. Each instrument contributes a unique dimension to the dataset, from infrared spectroscopy, revealing chemical composition, to imaging that maps the three-dimensional structure of the coma and tail. In this sense, the observational windows themselves become a narrative of scientific coordination, reflecting both the challenge and the promise inherent in studying a transient interstellar visitor. Ultimately, these windows are fleeting gateways into understanding. They transform a distant, enigmatic object into a subject accessible to rigorous study, allowing scientists to probe the mechanisms that govern its anomalous behavior. Through these observations, researchers can refine models, test predictions, and deepen understanding of interstellar object dynamics, setting the stage for conclusions that may illuminate both natural processes and, potentially, subtle indicators of artificial intervention. 3I Atlas, in its passage past Mars, offers a final, concentrated period in which its secrets may be more fully revealed, linking precise observation with profound scientific inquiry. The Vera C. Rubin Observatory promises to transform our understanding of interstellar objects, offering unprecedented capability to detect, track, and characterize these fleeting visitors. With its wide-field survey and high cadence, Rubin will capture the entire southern sky every few nights, producing a decade-long cinematic record of dynamic phenomena. For objects like 3I Atlas, this capability translates into early detection, rapid confirmation, and continuous monitoring, providing the temporal and spatial resolution necessary to understand subtle anomalies in activity, chemical composition, and trajectory. Where previous surveys relied on chance or incremental coverage, Rubin enables systematic observation of interstellar visitors, dramatically increasing the likelihood of capturing both rare and extreme behaviors. Early detection is particularly significant for unusual objects exhibiting anomalous dynamics. 3I Atlas demonstrates that activity and non-gravitational acceleration need not align in predictable ways. Rubin's consistent, high-resolution imaging would allow astronomers to observe similar objects from initial detection through perihelion and beyond, documenting changes in coma morphology, tail formation, and rotational state. Continuous monitoring provides a temporal dimension that is critical for distinguishing transient phenomena from persistent anomalies, offering insight into vent symmetry, rotational averaging, and chemical evolution. This temporal fidelity transforms interstellar object studies from episodic curiosity into systematic science. Furthermore, Rubin-era observations facilitate statistical analysis of interstellar object populations, with dozens of objects expected to be detected annually once the survey reaches full capability. Researchers can quantify the frequency of anomalies like those seen in 3I Atlas. Comparing activity patterns, chemical compositions, and dynamical behaviors across a statistically significant sample allows scientists to differentiate between rare natural configurations and potential artificial signatures. This comparative framework enhances understanding of the diversity of interstellar material and informs probabilistic models, situating 3I Atlas within a broader context of cosmic extremes rather than as an isolated outlier. Finally, the Rubin Observatory exemplifies the integration of technology, strategy, and scientific ambition. Its ability to detect, track, and characterize interstellar visitors systematically provides not only an empirical foundation, but also a strategic roadmap for future SETI and astrophysical investigations. By identifying anomalies early and enabling coordinated follow-up, Rubin expands both the observational and interpretive horizons, ensuring that extraordinary objects like 3I Atlas can be studied in depth. The observatory thus represents a convergence of precision, scope, and foresight, transforming transient cosmic phenomena into enduring opportunities for discovery and insight into the mysteries of interstellar space. At the intersection of natural extremity and speculative possibility lies the question, is 3I Atlas a cosmic oddball or a carefully engineered artifact? The object embodies characteristics that defy conventional expectations while remaining consistent with extreme natural configurations. Its CO₂-dominated outgassing, isotropic venting, and rotational averaging combine to produce dynamical stability at the hyperbolic speeds characteristic of interstellar passage. These features could arise from improbable yet physically plausible circumstances: a massive, slowly rotating nucleus with finely balanced vent distribution. Within this framework, the object is an extraordinary example of interstellar cometary diversity, a rare convergence of mass, chemistry, and dynamics that challenges models calibrated on the more familiar solar system population. Yet the alternative remains: could the object be artificially stabilized? The precision of vent symmetry, the absence of measurable acceleration despite vigorous activity, and the nickel-rich chemical signature invite the hypothesis of intentional design. In this scenario, 3I Atlas might represent an interstellar probe or observational platform, engineered to maintain trajectory while permitting controlled venting for thermal management or data collection. Such a possibility, while speculative, cannot be entirely excluded based on current evidence. It exemplifies the frontier of scientific inquiry, where anomalies force a reconsideration of both natural variation and the potential manifestations of extraterrestrial engineering. The tension between these interpretations underscores the philosophical dimension of the mystery. If natural processes are sufficient, 3I Atlas illustrates the remarkable diversity and subtlety of interstellar material, emphasizing that extreme configurations can produce behavior that appears paradoxical from our limited perspective. If artificial mechanisms are involved, the implications are profound, suggesting intelligence capable of interstellar navigation and engineering beyond current human experience. In either case, the object challenges assumptions, compelling both scientific rigor and imaginative engagement with the data. Contextualizing 3I Atlas alongside previous interstellar visitors reinforces the uniqueness of its behavior. Oumuamua accelerated without visible outgassing. Borisov followed predictable cometary dynamics. And now 3I Atlas outgasses without detectable acceleration. This inversion and complementarity of anomalies illuminate the spectrum of interstellar object behavior, highlighting the potential for both extreme natural variation and, conceivably, engineered intervention. Each object serves as a case study, expanding understanding while maintaining a core tension between expectation and observation. Ultimately, the cosmic oddball versus engineered artifact question frames the object within a broader narrative of discovery, speculation, and human interpretation. It exemplifies how interstellar visitors can stretch the limits of knowledge, challenge assumptions about physics and chemistry, and inspire reflection on intelligence, design, and natural extremity in the cosmos. 3I Atlas thus occupies a liminal space, a messenger of possibility, a laboratory of extremes, and a catalyst for the profound contemplation of what interstellar phenomena can reveal about the universe and our place within it. The philosophical reflections prompted by 3I Atlas extend far beyond cometary physics or interstellar dynamics, touching upon humanity's place in the cosmos and the nature of observation itself. In observing an object that exhibits paradoxical behavior, active outgassing without measurable acceleration, unusual chemical composition, and precise vent symmetry, scientists confront the limits of knowledge, the probabilistic nature of physical extremes, and the possibility that intelligence may manifest in forms not previously considered. Each observation becomes both a data point and a meditation, a reminder that the universe operates independently of expectation, revealing truths that challenge assumptions and expand understanding. Contemplating 3I Atlas encourages reflection on the interplay between scale, perspective, and perception. The object, a city block-sized traveler from beyond the solar system, moves silently through the interstellar void, its processes governed by forces and chemistry that we can observe but not fully manipulate. Its stability amid vigorous activity illustrates the subtlety of physical laws, the delicate balance between mass, venting, and rotation, and the hidden mechanisms that govern motion at cosmic scales. The juxtaposition of observable behavior and inferred dynamics evokes a sense of wonder and humility. Even in an age of advanced instrumentation, the universe retains its capacity to surprise, confound, and inspire philosophical contemplation. At a broader level, 3I Atlas prompts consideration of epistemological boundaries. How do we interpret phenomena that exist at the extremes of natural law or the potential thresholds of technology? What constitutes sufficient evidence to distinguish between rare natural configurations and deliberate engineering. The object exemplifies the tension between skepticism and imagination, empiricism and speculation, illustrating that observation alone does not fully resolve uncertainty, and that inquiry must embrace both rigor and openness. In doing so, it becomes a mirror for human curiosity, reflecting the limitations of perception while inviting expansive thought about possibility and design in the cosmos. Finally, 3I Atlas serves as a quiet reminder of the poetic dimensions of discovery. Its passage through the solar system is a transient event, a fleeting intersection of matter, light, and consciousness. Observers witness a phenomenon that is simultaneously ordinary ice, sublimating into space, and extraordinary, defying expectations and inspiring questions that resonate beyond science into philosophy. In the silence between stars, the object whispers lessons about patience, observation, and the humility required to engage with a universe far older and more complex than our models suggest. Its mystery remains unsolved, yet its existence enriches understanding, challenging both intellect and imagination. In the end, the study of 3I Atlas illuminates the profound dialogue between the universe and humanity. It reminds us that anomalies are not merely curiosities but opportunities for reflection, that the boundaries of knowledge are as instructive as the truths discovered, and that in observing the cosmos, we participate in a narrative that intertwines fact, speculation, and wonder. The object departs as silently as it arrived, leaving behind questions, inspiration, and the enduring invitation to look upward with both rigor and reverence. The passage of 3I Atlas gradually recedes from view, slipping beyond the reach of telescopes and leaving only the faint traces recorded in light and data. Its journey through the solar system is fleeting, yet the observations it leaves behind continue to resonate, echoing in the minds of scientists and dreamers alike. Each photon captured, each spectral line measured, and each subtle motion recorded forms a tapestry of evidence, a quiet testament to the complexity and beauty of interstellar phenomena. The comet, or probe, or whatever form it may embody, reminds us that the universe is vast, indifferent, and profoundly intricate, offering glimpses that inspire both awe and reflection. As the light fades, one is left with a sense of continuity and impermanence intertwined. The mystery's 3I Atlas embodies its suppressed acceleration, its CO₂-driven activity. Its anomalous chemical signatures persist in data, in thought, and in the ongoing questions they provoke. They invite patience, careful analysis, and philosophical wonder, illustrating that even transient cosmic events can have lasting impact on understanding. In contemplating these phenomena, one feels the delicate balance of observation and imagination, where the universe reveals itself through subtlety and persistence, demanding both curiosity and humility from those who seek to know it. The object's departure is a reminder of the ephemeral nature of encounter and the enduring resonance of mystery. Though it moves onward into the interstellar void, the lessons it imparts about physics, probability, the limits of human understanding, and the possibility of intelligence beyond Earth linger, shaping perspectives and inspiring continued inquiry. In this quiet reflection, there is both reassurance and wonder. The cosmos is immense, its secrets intricate, yet through patience, observation, and thoughtful engagement, humanity glimpses the extraordinary. The voyage of 3I Atlas closes one chapter, but opens countless others, each inviting us to look upward, to question, and to marvel at the enigmatic beauty of the universe. Sweet dreams,